Hi. This lecture video will explain quadratic form or a quadratic function and how to complete a square in the Euclidean space. Today we look at a simple function that extends from a function of scalar. Okay, we start from what we know. If suppose you have x plus y square, everyone know that it can be expanded to x squared plus 2xy plus y squared. Okay, but now we would like to basically give you a tutorial so that you can be more familiar how this quadratic form can be extended to a function of a vector. So now let's say x and y are both vectors. X and y are both vectors in Rn. A similar form of this when you extend to a Euclidean space would be something like this. Okay, and if you expand just by ordinary matrix multiplication, you would know that is x transpose x plus y transpose x plus x transpose y plus y transpose y. Okay, first x and x, second x and y and x, and finally is y and y. Okay, so this is not hard at all. So how about considering a quadratic function? Okay, this is quadratic function in x that you will see a lot in in optimization in the form of Gaussian PDF distribution and a lot of things. Okay, a lot of engineering application involves with this quadratic function in variable x. Okay, so here we given that let's say u in Rn A is supposed to be a symmetric matrix. Okay, all right. And we also assume that A is invertible. Okay. The assumption that assume the symmetric property is very general, because there is one known fact that even though A is not symmetric, okay, even if A is not symmetric, what would happen? You would see that this is just by looking at the the size of this quantity. X is n by 1, A is n by n, X transpose is 1 by n. So this is just a scalar value. Okay, so if it's a scalar value, of course, it's equal to its transpose. So I can just I know that it's equal to itself plus itself transpose, and I just divide it by 2. This is the same thing because this term is just a scalar. But then if you consider the second term when you transpose this guy, is actually x transpose A transpose x divided by half. Divided by 2. So it's x transpose A plus A transpose x divided by 2. In this calculation, you will see that even though A is not symmetric, but the quadratic form of x that is parameterized by A is actually the same as using the symmetric part of A, or the red box. That is the same as using the symmetric part of A in the quadratic form. Why do you call this guy? Why do you call the red box as a symmetric part of A? Because any matrix A, of course, it can be written as this, right? Any A can be split into 2 parts. This part is always symmetric, but this part is always skew symmetric. Okay, skew symmetric means if B is skew symmetric, it means that B equals minus B transpose. Okay, so just a short introduction that whenever we consider a quadratic form in X, okay, typically the matrix that parameterize that quadratic form is assumed without loss of generality will be assumed as symmetric matrix. Because even is not symmetric, you can just take the symmetric part of A. Okay, now I'm just going to erase this part. Okay, what else? Now let's go back to the quadratic form. How about kind of, get used to it and expand this quadratic form together? Just a regular, matrix vector multiplication. You just look at each term and just multiply it out by noticing that, of course, when we if you just go back to this example, you will see that there are two terms. There are two terms of the crossing terms that are always equal to each other. Y transpose X and X transpose Y. This is just a scalar, and they are the same. So a lot of time, this will be just group two of X transpose Y. Okay, now we're gonna do the same thing. How about just expand everything? Now I'm gonna multiply X first. Okay. Okay, it's gonna be X transpose AX. Okay, plus with the minus. Next, so it's gonna be the crossing term minus X transpose AU. Okay, now I'm gonna take a look at U. Okay. So it's going to be minus U transpose AX, okay, plus U transpose AU. Okay, and now with the same thing. You see, this is quadratic form because the quadratic form in X, because it appears like, multiplication of X twice. So it's kind of, give the sense of squared. And of course, there's going to be what we call a linear term in X that, that appears because X will be multiplied with a constant. A and U are constant, are given matrices and vector. And of course, how about this subterm? What about its relation? X transpose AU. If you transpose the whole thing again, it's actually U transpose A transpose X, but A is symmetric. So this guy is actually the same as this. So it's actually X transpose AX minus 2, okay? Minus 2 U transpose AX plus U transpose AU. The multiplication of, the expansion of the quadratic form in X always, always go from step by step like this all the time. You will see quadratic function in X, linear terms in X with a factor of 2. This factor always appears because of the crossing term. Okay. Now, once we get once we get used to expanding the square, how about now I'm just going to erase the whole thing. Now, I would like just to spend 10 minutes to review about how we completing the square and how to extend it to the square of a function of several variables. So given that you know that x minus y square is x square minus 2xy plus y square, completing the square is a concept like this. If I have x minus, hold on. If I have x squared plus 4x plus 6, can you complete the square? Okay, from this relation, you will see that it is x plus 4 square. Okay, you get the factor of 2 because you know that 4x is 2 times 2 times x. The factor 2 here, you know that it always show up shows up because of, you know, when you expand the square. So that's why the factor that's why you get the number 2 when you're completing the square. But then you need to kind of make the compensation of the constant so that both sides of the equation equals. Here you know that from the last term it's going to be plus 4, but you have plus 6 on the left hand side, so you put plus 2 on the right hand side. Okay, so this is not the perfect square because you have the constant. The perfect square means something like this. Okay, because you know that this is x plus 4 square. This is the perfect square. Okay, now, so basically the whole thing here is just about how can you completing the square when we deal with the function of vectors. I'm just gonna give an easy example first. How about if I have x minus a transpose x minus a? Now my x, my a are of course a vector in Rn. Okay, and now I have also a constant vector w. Okay, and now I have this function. Okay, so this function is clearly quadratic because of the first term. Even though the second term is linear, but it is add up with a quadratic function, so the whole thing s is a quadratic form of x. Now, can you complete the square? Which means can you write it as, you know, x minus some constant vector, you know, and then x minus some constant vector? It may be possible that you need to add up something which is a constant, so that both sides of the equation equals. Of course, by using the same concept, when you complete the square, you notice that 2w transpose x, I already give the factor 2 here so that it's easy for you to see that you should start with x minus a. So the last term here, I should because of the last term, it should be constant, but it's going to be constant that when you multiply everything out, it's going to be, you know, a linear function in x when you multiply with x on this hand side, on this side. So I know that because of the factor 2 I already give, so I know that I should put w transpose. Okay, so let's expand it and to see how it turns out, and you know how which constant term should we add up to make the whole thing equal to s. All right, so I know that this guy, so I'm just going to group into two terms. So I know that the yellow term, when you multiply it out, when you multiply this guy, it's going to be this term, right? And x minus a transpose w plus w transpose x minus a plus w transpose. Then you see that okay, here you know that you already get 2 w transpose x, right? And you get minus 2 a transpose w plus w transpose u. Therefore, your S should be equals to x minus w transpose, x minus w transpose. Okay, and now you see this is the green term is a term in S. Okay, so how can you compensate this? So I should add back to a transpose w, and I should subtract w transpose. So this is how you complete the square of this term. Okay, so it's gonna give you the quadratic form in x. Okay. One more example. One more example. How about um, how about if I have x minus a transpose, okay, and I have a matrix here, sigma inverse, okay. I have another linear term. Okay, now my a and omega are given are vectors in Rn. My sigma is of course is a symmetric matrix. Okay, the question is of course clearly this is quadratic function. Okay, this is quadratic function. This is linear in x, but I want to group the whole thing. I want to express it as a square. Okay, the whole thing, the whole thing, I mean, basically S, which means I want to represent S as X as X minus some vector transpose and some matrix, right? And X minus some vector. And again, it may be, it may contain some constant. Okay, I should use another symbol. Okay, this is how you complete the square. Now let's see, by using the same observation from previous example, how do we start? So because the first term is already in the quadratic form, but it has a linear term here, so you may you should try to see how can you express W transpose X, you know, and how can you like make it to appear in the quadratic form that parameterized by sigma inverse. Then you would notice that W transpose X is actually equals W transpose sigma inverse X. Why would I try this way? Because I know that, so I'm going to start with, of course, the term that from the original, okay, but I know that the term that I'm supposed to put here, the box, is going to be multiplied with sigma inverse and then multiply with X. I know that the box here should be something related to W, right? But because it is multiplied with sigma inverse first, so then I try to think first, W transpose X should be here, multiplied with sigma inverse and then X. Then in that sense, I know that the term that I should put into the bracket should be sigma W. I mean, I swap the I mean, it looks like I transpose this term because I know that this is sigma W transpose sigma inverse X. So I put sigma W here. Okay, now, so this term should be the same. Now let's expand it. Let's expand it. Okay. So now you're gonna have this guy equals to X minus A transpose sigma inverse X minus A. Okay. Again, I try to look at this term together and sigma. Okay. The second term should be the crossing term between yellow and the green. Okay, so it's going to be, now I'm going to put a factor 2 immediately because I know that the crossing term between, yellow and the green, it will appear twice. So it's 2x minus a transpose sigma inverse sigma W. Okay. And then what's next? It's going to be the green and the green. Okay, so it's going to be W transpose sigma inverse sigma W. Okay, now let's see. once you expand it, you just need to compare it with S. Okay, compare with the existing term and to see how you would compensate with the when you complete it. So here you're gonna have plus 2, okay, W transpose X, okay, minus 2 what, A transpose W, okay, plus what, W transpose sigma W. Okay, what are the terms that 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 are contained in the original S? Of course, these and these, which mean your S, the term that you would like to complete the square. So it's going to be this, okay. It's going to be the orange box, okay. But then you need to compensate it. So it's going to be plus 2A transpose minus W transpose sigma W. And this is this is how you complete the square. Now this is not a perfect square because somehow it remains some constant term in the green box. Okay. I hope you understand the video. We're gonna use this again in many places of the analysis. The the one that we can apply immediately is when you compute or when you analyze the characteristic function of a Gaussian vector, or when you have in optimization you have quadratic function, and then you have some linear term. Okay, you immediately recognize this is quadratic function. When you complete a square, basically you try to formulate the cost objective into a perfect quadratic form, because you know that the second term when you do the optimization in X will not be relevant. Okay, that's an example that I can say right now. All right, I would like to end the video, this tutorial video now.